In this video, we look to introduce linear transformations. In math, generally when we study a category of mathematical objects, typically we also want to look at the functions between objects in the category that preserve the structure of those objects. Here I've put the word category in quotes because there's actually a technical mathematical definition of what a category is, but that's beyond the scope of this course. Okay, so in linear algebra, the objects that we look at are vector spaces, and their structure is given by the operations of vector addition and scalar multiplication. So what that means is we want to study functions between vector spaces that somehow preserve these two operations, which we'll discuss in a little bit. So these are what we're going to call linear transformations. However, before we introduce linear transformations, let's go over some of the terminology that applies to any kind of function. So first of all, there are three parts to a function, right? So there's going to be a set A called the domain, a set B called the codomain, and the function itself. So this is the notation we use to describe a function. Right, so again, the function itself together with two sets A and B. And so a function is a mapping that associates to each element of the set A, called the domain, exactly one element of the set B, which is called the codomain. So one thing to be careful about here is that the codomain of a function is in general different from the range of a function. So you don't want to confuse those two definitions. Okay, so typically when we specify a function, we also specify how the function is calculated, right? So we write f of a is equal to b when an element a in the domain is associated to the element b in the codomain. And this element little b is called the image of the element a. So as I mentioned previously, when we specify a function, we need to specify all three parts, right? So what the domain is, what the codomain is, and the function itself. The next definition is the range of a function. So the range of a function is all the elements of the codomain that has something that maps to it, right? So basically, if you vary A among all the elements of the domain and look at all the results from calculating the function, so all the results that lie in the codomain, this forms the range of the function. And then finally, the preimage of an element in the codomain is a set of all elements in the domain which map onto the element little b. So that's another thing you want to be careful about in terms of this terminology, right? So in general, the image of an element A is a single element in the codomain. So here the image is little b, which is a single element. However, the preimage of an element in the codomain is a set of elements in the domain. Okay, so let's look at an example of a function, a real valued function here. So here the domain A is the set of real numbers, and B, the codomain B is also the set of real numbers. And I've defined the formula for the function to be f of x is equal to 2x minus 5, right? So that's how we calculate the function. So for example, say I want to calculate the image of, say, the number -1. Right, so here -1 is taken to be in the domain. So the image should be in the codomain, and I calculate the image by just plugging it into the function. And then calculating, right? So here x is -1, so I plug it in for x. Right, so the image of -1 is the element -7, and this belongs to B. Okay. So that's how we can calculate the image. So next, let's look at the range for this function. Right. So the range should be a set, and it's a subset of the codomain. Right. So we want to find out all the elements in the codomain that have something mapped to it from the domain. Right. So to find the range, so take an arbitrary element in the codomain. Right, so I don't want to take a particular element. I want to take an arbitrary one, which could be any real number, and I want to be able to calculate this number using the function. So so for B to be in the range, we need to be able to solve f of A is equal to B. Right, but then f of A is just given by the function. So 2a minus 5 is equal to B. And this can always be solved, right? Because I can just use algebra to solve for A. So A is equal to B plus 5 over 2. And so because this can always be solved for any B, that means that the range is all of the codomain. Okay, so that's the range. And finally, let's look at the preimage. So say the element 0. Right, so here I'm taking 0 from the codomain. So I need to find all the elements that map onto 0. So I just need to solve the equation. 2a minus 5 is equal to 0 tells me that a is equal to 5 halves. And this is the only solution to this equation. So the preimage is the set containing this one element. Okay. So that's an example going over the different terminologies associated to a function. Okay, so we said that we want a linear transformation to be a function between vector spaces that preserves the operations of vector addition and scalar multiplication. And these two conditions are exactly what we mean by that, right? So again, a linear transformation is a function between two vector spaces, V and W, right? So V is specified as the domain and W is specified as the codomain. And what it means to preserve vector addition is that if you calculate the linear transformation by first taking the sum of the two vectors in V and then applying the transformation, it's the same as if you applied the transformation to the two vectors individually and then do the vector addition in the codomain, right? So that's one thing you want to pay attention to here, right? So this addition is the vector addition for V because it's applied before the transformation, and this addition is applied after the transformation, right? So now we're belonging to the vector space W, and so this addition is the vector addition for the vector space W. And then similarly for scalar multiplication, right? So this scalar multiplication occurs in the vector space V, and then this scalar multiplication occurs in the vector space W. Okay, so here we have an example of a function between two vector spaces, and we want to verify the two conditions to see that it is a linear transformation, right? So we have a function from R3 to R2, right? So this is my V, this is my W, and the transformation is given by so a 3-coordinate vector x1, x2, x3 is transformed into a 2-coordinate vector by doing the calculation specified here, right? So first, if I want to verify condition 1, right? So we take U and V, so be arbitrary elements in V. Let's call it U1, U2, U3. And then V, vector V, also should be in V. Okay, so these two elements are both in the domain. And now I have to check this calculation. Right, so first, the left-hand side. So U plus V, so this vector addition occurs in the domain. Right, so I add the two vectors first before transforming them. Right, so adding the two vectors is just the sum of their components. and then now I transform this, right? So now I apply the formula for the function, right? So here the first component x1, x2, x3, and it's calculated this way, right? So this is playing the role of x1, this is playing the role of x2, and this is playing the role of x3. Right, so now I just plug it into the formula, and the result is the following. So this is x1, then minus x2, which is this, plus x3, which is this. So that's the first component, and then the second component is 2x1 plus x2, and then minus 4x3. Okay, so that's the result of the left-hand side. Now I have to compare it to the right-hand side. So T of U is just transforming U1, U2, U3, and T of V is just transforming V1, V2, V3. Okay, so I transform them separately, right? So I apply this formula to U1, U2, U3. So that gives me U1 minus U2 plus U3, comma, 2U1 plus U2 minus 4U3. And then now I transform this. So apply it to V1, V2, V3. So you get V1 minus V2 plus V3, comma, 2V1 plus V2 minus 4V3. Okay, so then now I have to do the vector addition. Right, so each of these vectors has two components, right? So this is the first component, second component, first component, second component. So I add the corresponding components together. Right, so this plus this. So U1 minus U2 plus U3, so that's the first component on the left, and plus the first component on the right, so V1 minus V2 plus V3, and then I add the second components together, so 2U1 plus U2 minus 4U3 plus 2V1 plus V2 minus 4V3. And you'll see that this is exactly the same as this, right? So I just need to rearrange the terms together. Right, so this is U1 plus V1 minus U2 plus V2. Right, so minus minus, I can factor out the minus, and plus U3 plus V3, and comma. Then these two terms go together, so 2U1 plus V1 plus U2 plus V2 minus 4U3 minus V3. Okay, and then you can see that this is exactly the same as this, so condition 1 is satisfied. Okay, so now we verify condition 2, which is for the same thing for scalar multiplication. Right, so I have to first calculate the scalar multiplication occurring before the transformation. So let's CU1, CU2, CU3. But if I apply to the transformation to this, what do I get? Right, so this is basically the formula here, right? So So you get CU1 minus CU2 plus CU3, comma, 2CU1 plus CU2 minus 4CU3. Right, because this is x1, this is x2, this is x3. Okay, so then now calculate the right hand side, which was C times T of U. So that's C times basically this thing, right? So U1 minus U2 plus U3, comma, 2U1 plus U2 minus 4U3. And then scale multiplication just means you distribute it, right? So CU1 minus CU2 plus CU3, comma, 2CU1 plus CU2 minus 4CU3. And then you can see again that these two things are the same. Okay, so this shows that this is a linear transformation. Okay, so continuing with the same function from before, which we now know is a linear transformation, we want to look at how to calculate the image and preimage of some element. Okay, so here we want to calculate the image of this element in the domain. Right, so this one belongs to the domain. So to calculate the image of something, we just plug it into the function. Right, so t of 2, 0, comma, negative 1 is my x1, x2, x3. So I just need to plug it into the formula and calculate. Right, so what do I get? So x1 minus x2 plus x3, which is going to be 2 minus 0 plus a negative 1. And then 2x1 plus x2 minus 4x3. So plugging in the numbers, I get 2 times 2 plus 0 minus 4 times negative 1. And calculating, so 2 minus 1 is 1. And then 4 plus 4 is 8. Right, and then this belongs to the codomain. Okay, so the image of an element is a single element. Okay, so now let's try to calculate the preimage of something. So this belongs to the codomain. So finding the preimage of something means finding all elements in the domain. Say x1, comma, x2, x3, such that T transforms this vector into the element that we want. Right, but then the transformation T is just given by this formula, right? So we can set it equal to the element. But then these two things are equal when their components are equal. Right, so first component we get x1 minus x2 plus x3 is equal to 1. And second component is equal to 8. Then what we have here is just a system of equations which we can now set up as an augmented matrix. Right, so this is the augmented matrix. And then, so to solve this, we look at the row reduced echelon form, which is calculates to exactly this. Right, so we first locate the leading ones, right? So first row, leading entry is here. Second row, leading entry is here. So column this for x1, this column's for x2, this column's for x3. Right, so the column for x3 doesn't have a leading one, so that means that x3 is a free variable, which we can parameterize as t. And so now what do the rows say? Row 1 says that x1 minus x3, which is t, is equal to 3, and then row 2 says that x2 minus 2x3 is equal to 2. Okay, so this gives me x1, this gives me x2, x3 was t, and then this gives me x3, right? So what do I have? x1, x2, x3 is equal to, x1 is here, right? So x1 is 3 plus t, x2 is this, which is 2 plus 2t, x3 is this, which is t. Right, so the solution is a set of vectors that look like 3 plus t, 2 plus 2t, comma t. Okay, so one thing you should notice about the solution here is, right, so the preimage of this element now, in this case, has infinitely many vectors, because t can vary as any real number. But if you compare the first part to this part, right, so in the first part we calculated that the image of this vector is the vector 1 comma 8, right? So if we turn around and try to find the preimage of this vector, at least because this vector transforms into this, right? So the vector 2 0 negative 1 should be part of the preimage, right? Which is the case, right? Because is to get this vector, if I take t to be negative 1, right, so then the third component would be negative 1. Then the second component would be 2 minus 2, which is 0. And then again, if t is negative 1, then the first component is 3 minus 1, which is equal to 2. Right, so when t is negative 1, you get back exactly this element. But the preimage in this example consists of other vectors than just this single vector. Okay. So in the second example on this page, we're looking at the function we discussed in the first page. So the function f of x is 2x minus 5 from the set of real numbers to itself. So the claim here is that this is not a linear transformation. Right, so to see that it's not a linear transformation, we check the two properties, right? So the two conditions, right? So condition 1, so say I calculate f of x1 plus x2. What is this? So this just goes in for x, right? So it's 2 times x1 plus x2 minus 5, which is 2x1 plus 2x2 minus 5. But if I calculate it the other way, so f of x1 plus f of x2, what is this equal to? So I transform x1, that's 2x1 minus 5, and then I transform x2, which gives me 2x2 minus 5, and then if I put this together, I get 2x1 plus 2x2 minus 5, which gives me minus 10. Right, so you can see this is not the same. So condition 1 fails. What about condition 2? So condition 1 fails. Okay, so now let's check condition 2. So if I do the scalar multiplication like this, what do I get? I get 2c times x1 minus 5. And then if I do the scalar multiplication like this, what do I get? So I transform first, right? So that's 2x1 minus 5. And then I scalar multiply by c. So what does this look like? It looks like 2c x1 minus 5c. But again, you can see that this and this is not the same. And so condition 2 also fails. Okay, so we see that the function f of x is equal to 2x minus 5 is not a linear transformation. Right, so you want to be careful about the terminology here, right? So we have a linear function, right? So 2x minus 5 is usually, right, because it's in the form mx plus b, it's usually thought of as a linear function, right? But this linear function is not a linear transformation between vector spaces because it doesn't satisfy these two conditions. Okay. So sometimes not confuse the word linear between the two. Sometimes this is referred to as an affine transformation. Okay, so so in example 3, we look at another kind of linear transformation, right? So if we have our domain as the vector space Rn and the codomain as the vector space Rm, then we can form a linear transformation using any matrix A and performing the matrix multiplication like this, right? So this is just matrix multiplication. So transforming a vector x is just multiplying on the left a times x, right? So everything here makes sense, right? Because A is an m by n matrix, x being a vector in the domain, because that's the input, right? So x is the input. So that means it's part of the domain, which is an Rn, which we think of as a column vector. So as a column vector, that will be n by 1, right? And so because these numbers match up, the result is an m by 1 vector. Which means it's in Rm. Okay, so you can easily see that this is a linear transformation just from the properties of matrix multiplication, right? So T of u plus v means multiplying, so I apply, so u plus v goes in for x, right? So you have a times u plus v, but matrix multiplication is distributive, so this is just au plus av, so then this is just transforming u and v separately. And then similarly for scalar multiplication, this means multiplying on the left by a, but then c is a scalar, so I can just pull that out. And this is just transforming u first, and then multiplying by c. Okay, so we can construct a linear transformation of this form by just multiplying by an m by n matrix A. On this page, we look at two particular linear transformations given by matrices, right? So again, this type of linear transformation is just exactly the type from example 3, but we're looking at a specific matrix for A, right? So here we're taking A to be a 2 by 2 matrix, so the domain is R2 and the codomain is R2. And if A is in particular, so first you fix an angle theta, right? And if you take A to be the 2 by 2 matrix cosine theta minus sine theta, cosine theta, again, whatever theta is, you would calculate the trig functions for this angle, right? So like say 30 degrees or 60 degrees or 45 degrees or something. Then the transformation given by multiplication by this matrix represents a rotation going counterclockwise by the angle theta in the plane. So we can see that this is a counterclockwise rotation by representing things in polar coordinates, right? So taking a vector in R2, x and y coordinates, we represent in polar coordinates. So x is r cosine say alpha, and then y is r sine alpha. So I use alpha to be a different angle from theta, and then the transformation is just multiplying on the left by A, right? So here we carry out the matrix multiplication, and if you look at the x component and apply the cosine sum formula, it'll look like this. And if you look at the y component, you apply the sine sum formula, it looks like this. Right? And then so if you represent this, so the original vector, right, so x comma y is this compared to the transformed vector. So the initial vector has an angle of alpha with the positive x-axis, right, because that's how you represent an angle in polar coordinates, right? So r cosine alpha comma r sine alpha, right? So r is the radius of the circle, and then alpha is the angle of rotation from the positive x-axis. And so this is the transformed vector, right? So cosine theta plus alpha comma r sine theta plus alpha. And so now the angle is alpha plus the additional angle theta, right? So it's an additional rotation of theta. And so this vector is transformed into this vector. And so it's a rotation counterclockwise of angle theta. Okay, so we can represent rotations in the plane by using a linear transformation represented by this matrix. So if theta is positive, that means you're going counterclockwise. If theta is negative, it means you're going clockwise. Right, so negative theta means going clockwise. Okay. And in this next example here, we're taking this 3 by 3 matrix A, and the domain is R3, the codomain is also R3, and we look at what happens when we apply the matrix multiplication. So basically the x component stays the same, the y component stays the same, the z component becomes 0. Okay, so that's how the transformation looks according to the matrix multiplication by A. Geometrically what's happening is that if you take any point in three-dimensional space and you leave the x and y coordinates the same, but you make the z component 0, it projects everything down onto the xy plane. Okay, so because we know that function spaces can form vector spaces, here we look at some examples from calculus, right? So if we take this vector space, so it's C with a superscript 1 on the interval from a, b, so this vector space represents the vector space of all functions whose first derivatives exist and are continuous on the interval from a, b, right? So this is a slightly different vector space than C of a, b, right? Because that's just the vector space of continuous functions. But not every continuous function is differentiable. So we need to look at a slightly different vector space that has differentiable functions to be able to take the derivative. Okay, so by taking a look at differentiable functions, we can see that the derivative is a linear transformation. This is just from calculus, right? So the linear transformation is just given by on a function in this vector space is just given by taking the derivative with respect to x, right? But from calculus, we know that the derivative of the sum of two functions is the sum of the derivatives, and the derivative of a constant multiple, you can just pull the constant multiple out, right? So this is exactly the two properties for a linear transformation. And so we see that the derivative is a linear transformation for differentiable functions. And then similarly, if we look at the definite integral over the interval from a to b, so any continuous function on a closed and bounded interval is integrable, right? So so we can take the domain to be the continuous functions on the closed and bounded interval from a to b, and then the result of a definite integral is just a number, right? So then the codomain is just the set of real numbers. And so we can define a linear transformation by taking the definite integral of a function. And we know from calculus that the definite integral again obeys these two properties. So this is a linear transformation. And then finally, we have theorem 6.1 here, which just lists additional properties of a linear transformation. And so what we have is that these four properties essentially just follow from the original two conditions, right? Because if we take the scalar multiple property and take C to be 0, then you get exactly this first property here. If again you take this scalar multiple property and you take C to be -1, you get this property. And then 3 and 4 is just combining the two properties of scalar multiplication and vector addition together. So property 1 is especially useful because all linear transformations have to satisfy property 1 here, right? So an easy way to check to see if something is a linear transformation is to see if the 0 vector is transformed to the 0 vector, right? So going back to this previous example here, you can see that f of 0 is not 0, right? So f of 0 is not equal to 0. And so again, from this you can see that it can't be a linear transformation.